Let's take another look at the concept of temperature. In our look at heat engines, we equated the small incremental amount of heat rejected to the surroundings as equal to T times ds. In general, we can say that TdS is equal to the incremental amount of heat transferred reversibly in a system. If we transfer this heat at constant volume and number of moles, then no work can be done in the system, and so the amount of heat transferred is equal to the total change in internal energy. Substituting dE in for dQ allows us to determine that the temperature is the partial derivative of energy with respect to entropy. But what exactly does this mean? So temperature tells me how fast the energy of the system will increase as I increase the number of microstates in the system. To better understand what that means, let's look at two energy systems that we're familiar with. First, the particle in a box, and second, the hydrogen atom, electronic states. In both of these systems, and indeed in pretty much every microscopic energy level system, we can see that the number of states increases as we increase the energy. So the number of states in a small energy range is much, much larger at higher energies than it is at lower energies. So we might expect that if we look at the energy as a function of the entropy, that as the energy increases, the number of microstates increase, and therefore the entropy of the system increases. The temperature is the slope of the tangent to the curve at any point. Let's look at this in a different way. If I'm at a low energy state, then I don't have very many microstates available to me. I have to change the energy by a lot in order to make these microstates, more microstates available. So if we look at our temperature derivative, I have to change energy by a lot to get a modest change in the number of microstates. Thus, it requires a high temperature to make that change. However, if I'm already at a high energy, I only have to change the energy by a little bit to get a lot more microstates available because the microstates are much more densely packed up here. And so at the higher energy, if I'm already at a higher energy, a little tiny change in the energy makes a huge change in the number of microstates, and that means that I have a small temperature required to make that change. So the temperature is related to the density of states. The more densely packed the states are, the smaller the temperature. The less densely packed, the larger the temperature.